As we have read in thermodynamics, there are two processes. One is your reversible process, other is your irreversible process. Reversible process means after some working conditions, the initial state is identical with the final state. That is reversible. The initial state is identical with the final state, but in irreversible process, that is never identical. So likewise, in your elastic and plastic deformations, elastic deformation is a reversible process. That means after removing the load, the metal can regain its original shape and size. And the deformation is very less here. But we see here, in plastic deformations, there is a permanent change in shape. There is a permanent change in shape. There is no chance to regain its original shape and size again. So from the metal, giving the shaping of the materials, from the metal forming processes, or from the plasticity point of view, the metal forming process or the plasticity is very important because we are giving the shape to any metals for some particular, as you are considering for application point of view, that we are giving the shape of the shape the material, shape the metal. That means we have going for the plastic deformation. That's why the plastic deformation is very much important, very much important in our practical field of life. So and that is plasticity is that there is the inability of the metal to regain its original shape and size after the deformations. There is the permanent change in shape. That is the called as permanent change in shape. That is your plastic deformations. So when you are considering the plastic deformations, before you going to the why this is very important for you? Why you are studying this subject, the theory of plasticity? Why you are studying this? Because all the engineering materials, all the applications, as we are going to the application based category, then we will find that the plasticity plays a very important role. Because without plastic deformation, we don't have ability to give any shape to the metals. So that's why the plastic deformation is very much important than any other than the elastic deformation processes. And plastic deformation is also the very large deformation process. Plastic deformation is also the very large deformation processes. When we are talking about the deformation processes, there is one thing is very much important, that is that is called as your stress strain diagram. That is stress strain diagram. When we are considering the plastic deformation process, that is very important for here to the stress strain diagram. I think all of you are about the stress strain diagrams. All of you are about the stress strain diagrams. The stress strain diagram, what we have read or studied in B.Tech, that is called as, I think most of us not studying, most of you are not studying the true stress strain diagram. The stress strain diagram, whatever you studied, that is your engineering stress strain diagram. The stress strain diagram, what you have read, that is your engineering stress strain diagram. And there is a term that is called as true stress strain diagram. Then can have you that idea about what is that true stress strain diagram? What is the true stress strain diagram?
Sir, in the engineering stress strain diagram, we don't consider the change of the dimension, but in true stress strain diagram, we consider the change of the dimension with respect to the load.
So in true stress strain diagram, what happens? In engineering stress strain diagram, if you're going to show you something, just 1 minute, just 1 minute. Is visible to you? My screen is visible to all of you?
Yes, sir.
Okay.
Yes, sir.
So uh, when there is a, if there is a rod that is applied by the force load or tensile stress, tensile loading is the condition of tensile loading. The material will elongate. The material will, after the application of the load, the material will elongate in that manner. Material will elongate. Material will elongate with the force. Okay. Material will elongate. So in that case, what happens when we are writing the stress equation? What is stress is? Force per resisting force per unit area. That is stress. But the question is that after the when the elongation, when the load is applying continuously, the elongation going on increases. The elongation increases. When the elongation increases, when elongation increases, there is a shape change. That means the deformation increases. The dimension of the material will be decreases. The dimension means the area that will be changes continuously. With the increase in elongation, the area will be changes continuously. But when we are drawing the engineering stress strain diagram, we are not focusing on the change in area. Always we write this equation. In engineering stress strain diagram, what we do, always we write this equation, stress usual force per unit area, resisting force per unit area. We are not changing that area is the original area. This is the original area. This is the A we have taken. But that A will be changed from deformation to deformation, different deformation stages. But what we have done here, we are not considering that change in area. That is the main drawback of the engineering stress strain diagram. So what happens due to this concept? What will happen to the engineering stress strain diagrams? What will be happen there in engineering stress strain diagram then? So uh, is that this is the stress. If you putting that actual stress, then that will be force resisting force per change in area. If you am putting A0 there. So these two stresses will be different. This stress will be different. This stress will be different. That stress is called your engineering stress, and that stress is called your true stress. This is the main concept of drawing the stress strain diagram. So when we stop, sir. So Rakesh Pradhan, unmute. Sir, mute yourself. So if you share something here. So is it visible? My screen is visible to you? No?
Yes, sir.
Yes, sir.
So, thank you.
Yes,
Uh,
sir.
so when we are talking about the deformations, so deformation is there is two category. One is your temporary, or that is called recoverable, other is the permanent deformations. Okay, so in recoverable or temporary deformation, that is your called as the elastic deformation. It is time independent. The elastic deformation is time independent. It does not depend upon the time. Again, the plastic deformation is also the time independent. Eagle don't do any annotations on the screen. Okay. So first you join on your name. So participants. Join by your name. Change your name. Okay. Hmm. See here. See. The time independent, both the plastic and elastic deformations are time independent. And then if you are considering the time dependent concept here in both the permanent and the recoverable or the temporary deformation is called as the elastic deformation or the recoverable deformation, permanent is the plastic deformations. So if you are considering in both the cases time dependent is the inelastic deformation, that is under load. Then the elastic after effect after removal of the load. Okay. So time dependent is here in plastic deformation, that is a creep. I think all of you know about that what is creep. It is a property of the material. What is creep? So this is the normal differentiate between the temporary and the permanent deformation processes. In temporary deformation, there is time independent and elastic. Time dependent is inelastic and elastic after effect. Then in permanent, then time independent is plastic and time dependent is your creep deformations. So, if you are combining both the processes, the combination of recoverable and the permanent but time dependent, there is another term is called viscoelastic. Viscoelastic is combination of the elastic and the plastic deformation but time dependent. It is all about the deformation processes. We are not talking about the deformations. So, the mechanical deformation, there is the external load. If there is it is the object, this is the external load. During the application of the external load, there are the three cases must be happens there. One is the translation, then is the rotation, then is the deformation. When we are try to apply a load on a body, you apply yourself in your home. When you try to apply a force on a body, that body may start to translation, may be rotation, and may have the deformations. If you choose the deformation process, then deformation is the distortion and dislocation. Deformation is the combination of distortion and dilation. So distortion is that change in shape, and dilation is that change in size. So this is your deformation processes. Deformation has two aspects, that is the distortion and dilation. And distortion is the change in shape, and dilation is the change in size. So first see the what is that engineering stress and engineering strain. Load applied act over an area. Load applied acts over an area. Always, that is always true. So in engineering stress strategy, as I have already told you, that that is S is stress is written for the this is symbolized as S. Stress is load per unit area. This A0 is the initial area. A0 is the initial area, and this is stress and strain. Strain is change in length by original length. The change in length is L minus L0 divided by L0. L0 is the original area. L is the final area, sorry, final length. L0 is the initial length. This is strain, engineering strain. That is symbolized as small e, and that is change in length by original length, L minus L0 by L0. So this is your engineering stress and strain. But that is not true for the true stress and strain. As I have told you, that true stress strain diagram is something different. A true stress and true strain is something different. That is not equal to the engineering stress and diagram. Because why it is different? Because it depends on the incremental. It depends on the incidental, dimensional. The dimensions or the area that we are using here for calculation is the incidental. At that time, at a particular time, what will be the deformation that are using in this calculation? Not like the engineering station diagram that we are using that initial area throughout the calculations. That is not, but it is the incident. That particular incident, what is the area? That will be used in true stress strain diagram. So true or natural stress and strains are defined to give true picture of the instantaneous conditions. Instantaneous at the particular instance, what will be the dimensions that will be used in true stress strain diagram. So if you are talking about the true strain, that is symbolized as epsilon, and that is the sum of the, that is not the true strain is the sum of the incremental strengths, sum of the incremental strengths. See this, the first incremental strength, the L1 minus L0 by L0, the second, then again second, that is L2 minus L1 by L1. Similarly, L3 plus minus L2 by L2. The incremental, the sum of the incremental strength. So we can write down this equation as epsilon is equal to the integration processes, addition process. So L0 to L, initial length to final length, dl by L. So in that format we can write ln L by L0. Similarly, true stress is written as P by A. True stress is written as P by A. In that engineering stress, what we are writing there is that, just see here, in engineering stress we are writing sigma is equal to P by A0. P by A0. A0 is the initial area. The initial area, the initial dimensions, the initial area. But here when we are writing the true stress sigma t, that we are using the equation P by A. P by A is the instantaneous area. A is the instantaneous area or the area at the particular instance. Okay, so this is for true stress. This is for true stress. If you want to derive the relationship between the true stress and true strain to engineering stress and strain, so see this. The true strain, engineering strain is written as E is equal to del L by L, del L by L. That is L minus L0, sorry, L0, that is L minus L0 by L0. That is written in that format. We can write that in format also L minus 1. We can write in that format also E is equal to L minus 1. We can write in that format also. So see here, but engineering stress strain, what we have written here, the engineering stress true stress strain epsilon is equal to del dl by L integration over dl by, sorry, dl by L integration over L0 to L, initial length to final length. So that we can write in that format also ln is equal to ln by L by L0. We can write in that format. So if you see L by L0, what happens? I mean, when you are considering the engineering stress strain to true stress strain diagram, when you are considering the deformation processes, in deformation processes, the change in volume is always constant. The change in volume is zero. The change in volume is constant, always constant. There is no change in volume. There is deformations in plastic deformation. Remember this term. In plastic deformation, the change in shape is there. The change in shape is there. Size is there, but change there is no change in volume. Volume of the material is always constant, so there is no change in volume, but we can write the volume in the term also del V. Volume equals to area into length, that is volume. We can write this also A0 L0 also. This is the AL is the volume, final volume. This is the final volume, and it is the initial volume, the initial volume. So from this equation we can say that AL equals to A0 L0. AL equals to A0 L0. Due to the volume is constant, the volume before deformation and volume after deformation is always constant. So we can write down this equation AL equals to A0 L0. In the same format, if you want to write, then that we can write here. Just want to clear this all the drawings. So we find that A0 L0 equals to A0, sorry, uh, A L. So L by L0, we can write L by L0 equals to what? A0 by A. You can write in that format also. You can write in that format also. Okay. So epsilon is what happens? See this. Epsilon is ln L by L0. Ln L by L0. See here another concept here. And the true stress. See this equation. The true stress is sigma is equal to P by A. If sigma is equal to P by A, sigma is written as, the true stress is written as P by A. If I am multiplying A0, is that true or not? Is it true? In the same format, if I am writing P by A0 into A by A0 by A, I can write in that format also. In the last, what we have learned about that? P by A0, the force. The P by A0 is known as your the engineering stress. So you can write here the equation as P by A0 is the S, engineering stress S. And A0 by A. What is that A0 by A? What is that A0 by A? See here, this equation. A0 by A. A0 by A is the L by L0. A0 by A is the L by L0. So if you see the engineering stress strain diagram, engineering strain, then E is equal to L minus L0 by L0. So again I am writing this equation, already I have told one time, L by L0 minus 1. So L by L0 is E plus 1. E plus 1 is equal to L by L0. This is this, sorry. See this is one equation here. This is one equation here. This is another equation. This is first equation. See, this is second equation. Second equation. So, first equation says that L by L0 is equal to A0 by A. And second equation says that L by L0 is equal to E plus 1. So now we put the equations here. A by A0, sorry, A0 by A is the E plus 1. So now sigma, the true stress is equals to multiplication of engineering stress and engineering strain plus 1. বুঝিপারল এটা? Is it understandable? এটা বুঝিপারল
Yes, sir.
তো? Okay.
Yes, sir.
This relationship is very important. This relationship is very important. The relationship between true stress and true strains with the engineering stress strain. Okay. So I am clearing this board. So before you sit to the virtual classes, you must be with your pen and paper and write down what I have told you. This is very important. Without writing, or if you say you are taking the screenshot is not the solution here. Okay. So it is better for you to write down the equations. So this is here we have covered the true strain and true stresses, the relationship between true stress and true strains with the engineering stress strain diagram. So I think this is the different loads and strains as you have studied these things in B.Tech courses. So I don't go through this in details. So there is a elastic deformation. What is that elastic deformation? Means a material undergoes elastic deformation first, followed by the plastic deformation. The transition is not sharp in many instances. For most of the engineering materials, complete elastic deformation is characterized by strain proportional to the stress, that is called as Young's modulus. If you are taking that proportionality limit, that is your Young's modulus. Most of the cases in what is the stress is directly proportional to strain. If you are taking that, stress is equal to E epsilon. E is the Young's modulus or elastic modulus, that is whatever it's called. So non-linear stress-strain relationship is applicable for materials. There is a linearity. This is the linear relationships. Stress is directly proportional to strain, but there is also the non-linear relationship like the metals like rubber. Rubber is followed by rubber. As you know, rubber is very much elastic, but it is non-linear. It don't follow the proportional limit. Okay, or we can say that is the Hooke's law. That equation is derived from the Hooke's law. The stress is directly proportional to strain. That is Hooke's law. But the rubber don't obey the Hooke's law. Okay. So materials without a linear stress strain portion, either tangent or scan modulus is used to design calculations. And the tangent modulus is taken as the slope of the stress strain curve at the some specific level. Tangent. These are the tangents. The second modulus, that is also for the calculation, design calculation. This curve is used for the design calculation, the tangent modulus. Both the curves, both the moduluses are taken for the design calculations. Then elastic deformation, don't need to as you know, the theoretical basis of elastic deformation is the reversible displacement of atoms from their equilibrium positions, stretching of atomic bonds. Elastic moduli measures stiffness of a material, and from the elastic modulus we can measure the stiffness. Okay. It can also be a measure of resistance to separation of adjacent atoms.